Okay, so through your work of 1 through 6, you should have known when a function has an inverse. So I'm just going to go through that quick to help you out. Is that when a function has an inverse, every output has one distinct input. So another way to say that now with a function we've been looking, every x has a y. If a function has an inverse, then every y only goes back to one x value. We can check that on a full function with a horizontal line test. So if I had a parabola, for example, that doesn't have an inverse, but it may on what we call a restricted domain. We may say, okay, if this x is 3, we might say it does have an inverse when x is greater than 3, or maybe when x is less than 3. Because on those sides, then it does pass this horizontal line test, showing you that for each y, there's only one x. If I didn't have that, this same y value is going to this x value and to this x value. So what we want to find next is how to actually find that inverse equation. There's a paragraph in the book, hopefully you read also, about the notation. Is that we're trying to rearrange it so that I'm actually plugging in y values to get back to x values. So how we do that is we write this f inverse, but we still write it in terms of x. So that may look like this. So there's two strategies. I use strategy 2 here. That if I have a function g of x is 7 over x plus 4, what I'm going to do is I'm going to switch x and y first. So we'll say x equals 7 over y plus 4. And then I've switched essentially the roles of what x and y are, and I'm actually plugging in outputs. But then I want to solve for those inputs. So what I'm going to do is I'm going to solve this for y. Go by step 2, so we'll say x minus 4 equals 7 over y. From there, I can multiply both sides by y and then divide by x minus 4. I think hopefully we've seen this algebra enough. This is kind of a nice little switcheroo that we get 7 equals, or I'm sorry, y equals 7 over x minus 4. So now, again, I've switched the meaning of these. So this is actually my inverse. This is an input now. That's the input in the original function. So what I can say to change this notation is g inverse of x is 7 over x minus 4. So what you want to do is check to see if you've actually made the inverse. How I check to see if I made the inverse is if I plug in an x and get a y, I should be able to plug the y in to the inverse and get back the x. So I would say when x is 7, that would be a nice one in here, I would get a y of 5. 7 divided by 7 is 1 plus 4 gets me to 5. If I plug 5 into here, my inverse, I should get back to my original x, which was 7. Let's check it out. 7 divided by 5 minus 4 is 7. So I feel like my inverse works. So that's the gist of how you do this. You switch the x and y and then solve for y and put it in an inverse notation. But undoing functions can be a little bit difficult. So here's an example right off the bat. So I'm going to switch x and y. This is normally my y, so I'm going to switch it to x, and then I have y plus 3 cubed. So let's think about how I can undo this and solve for y. I have a multiplication first. I'm going to divide by -1. So I get negative x equals y plus 3 cubed. And again, I'm just thinking about how I undo stuff. So if I have a cubed, I would take the cube root. Another way of doing that is taking that to the 1/3 power, or both sides to the 1/3 power. And you can write it either way. I don't mind either way. But it's nice to think of these as exponents. So I get negative x to the 1/3. And the last step to solve for y is just subtract 3. So my y equals negative x to the 1/3 minus 3. But if I wanted an inverse notation, which we always do, don't leave it like this, you want m inverse of x to be negative x to the 1/3 minus 3. Okay, another situation, we got a rational function. We can find inverses of rationals. They might have a restricted domain, which is okay, but we can still find the function. And that restricted domain is already implied in here. x can't equal 1/3, so on and so forth. But switch x and y, and this one has shown to be usually the most troublesome algebraically. So we're going to multiply both sides by 3y plus 1. So then you get a 3xy plus x, which equals 2y plus 1. Now I have y's on both sides. If I've got y's on both sides, that's where the trouble comes in. A lot of students just kind of rearrange or divide by y, and not so much. If I have two y's, the only way I can get them into one y is by factoring. So what I'm going to do is I'm going to group my y's together. I'm going to bring my 2y to this side, and then subtract x to the other side. So I get 3xy minus 2y equals 1 minus x. From here, this is the little math magic. I got to get these two y terms into one term. So if I factor it out, notice that I'm just left with a y term. It's a 3x minus 2y term, but it's just a y term. It's 1 minus x. To get y alone, just divide by 3x minus 2, divide by 3x minus 2. So instead of y, I'm going to write n inverse of x, which is going to be 1 minus x over 3x minus 2. All right, the last thing we need to look at in this investigation is how to graph inverses. So they give you a table here, but I think I might start with the graphing here. That if I have a point 2, 3, that means my x was 2 and my y was 3. And what they want is all these points of the inverse. Well, think what you're doing. You're plugging in a y value to get back to the original x. So no matter what my inverse is, I should be plugging in my y to get back to my x. And that's the point that will be on the inverse. So in this case, if I plug in 3, 2, plug in y as 3, the inverse should get me back to the x of 2. Same thing here. 5, 1, 1, 2, 3, 4, 5, 1. So all of these have equivalent inverse points. So 0, 4 will go to 4, 0. So on and so forth, 2, negative 1, and I think you get the gist here, 1, negative 3. But what's helpful about this at negative 2, negative 1 is negative 1, negative 2, negative 3, negative 5. And I forgot this one here. We want a way that we don't want to find every single point, but if you start to see what's going on here is we're switching x and y. Like y equals x or x equals y. Well, we've done that in 2x where we had reflections, so this would be a reflection over the line y equals x. We're switching the role of x and y. So for any function to graph the inverse, switch x and y, or reflect over y equals x line. And what we think about is what that actually does to our domain and range, and that's what you want to do at the end of 8 here. I believe it asks you right here. So what I would want you to do in addition to this video is talk about the domain. Think about what the domain of these numbers are, just what x values they're dealing with, and then look at the inverse. Look at the range of the originals, and then look at the range of the inverse numbers. They have to have a relationship, so think about what that relationship might mean. Hopefully this helps out. We'll do a lot more rearranging of equations to find inverses. But again, an inverse should get you back to where you started. Functions, plug in x's to get to y's. Inverses, take y's and bring you back to x's. Hope that helps. See you later.